Okay, we started discussing a new type of formalism associated with quantum mechanics. And remember, we were working in the Hilbert space. Okay, and we are working with the Dirac notation. And we said that this was a very high dimensional space. Okay, the space can be in fact made up of a set of discrete set of basis vectors, or it could form a continuum. And our vectors, okay, state of the system is a vector which we represent by this notation. We called that a ket vector, okay? And there is also a dual space. So we have this psi ket, so let me use capital psi to represent that I am in Hilbert space. This is associated with our psi of x function in such a way that we can sort of graphically, okay, we are going to do somewhat better than this, but psi of x1, psi of x2, psi of x3, etc., a bunch of values like that, an entry in this vector for every value of psi. Okay, so you see that this is an infinite dimensional vector because x is a real number and it forms a continuum. So this is a rich space in that sense. Okay, we have a dual space. Okay, so we call this the adjoint space. Okay, so that's a different space from this one, but it's very similar in structure. And we show the vectors in that space like that. So that's remember, a bra vector. Okay, and that's a ket vector. They form a bracket when they come together. So this is something which looks like psi star of x1, psi star of x2, okay, psi star of x3, and so on.
So it's the Hermish. So it's the Hermish of vector.
Well, okay, if you look at it as a vector, it is the Hermitian adjoint of that vector. So I can in fact write this as this psi is this psi adjoint, okay? Or conversely, I can say that the adjoint of this psi is this psi, okay? So it's an adjoint operation which takes me from one to the other. We also defined an inner product. The inner product is if I have two such objects, for example, if I have a psi and a phi defined in this way, then what happens to this inner product? The corresponding things get multiplied together and the whole thing added up. So this thing is going to be psi of x complex conjugate because it's on the left, and phi of x dx for all values of x. Okay, so this is our definition of the inner product. All right. So what are the basis vectors. What are these vectors that we are going to expand this thing in? Well, x, we have already seen one of them. Okay, so we have this x1. Okay, so this is going to be a vector which is going to be all zeros except there's going to be a 1 at the position of x1 and so on. And this is x2. Obviously, it doesn't even make sense to write these in this form, but okay, so maybe I'll put the 1 over here. And x2 is going to be something like this, and so on. Okay, so this is going to be x3. But you get the idea that this, since this is a continuum, this is just a learning tool at this point. Yes?
You said that the capital of psi is infinite dimensional vector. Is that because we work on infinite dimensional Hilbert space?
Well, the Hilbert space has to be the dimension of this vector. So in this case, it is infinite dimensional. But we'll see that for certain systems, we'll look at, for example, the spin system. The spin system is a very small, cute system. It will only have 2 dimensions in its Hilbert space. Okay, so it's going to be a miniature quantum mechanics system. Okay, so we have that. Now, the basis, okay, for, okay, so let me in fact say orthogonal, normal basis for, okay, the Hilbert space. Okay, we'll take, okay, the eigenvectors of any Hermitian operator. Okay, so in this case, obviously we are looking at the x operator. Okay, so the x operator in the space is going to have as its eigenvector, say, some xi, which will give me xi times xi itself. Okay, so that's the position operator. Remember, we discussed the eigenfunctions of the position operator. So that's going to have its eigenvalues and eigenvectors. So these eigenvectors can form a basis for my, okay, for my Hilbert space. But I can also have a different set of, okay, basis vectors. For example, okay, so all of these x's are perpendicular to one another, although there are infinite number of them, so that's an orthogonal basis. But I could, for example, have chosen the momentum eigenvectors, right? So I could choose P1, P2. These things also form a continuum, P3. Okay, so that could also be a basis in which I can expand this psi. So I'll be expanding this psi in a number of bases, and I have to find a way of going from one to the other. Okay? A trick is to introduce an operator. Okay, so this is, for example, I can have that, or the momentum operator, pi is equal to pi. In fact, let me just use my k's. I have been using k for, well, h bar ki. Okay, so those are also possible basis vectors for expansion. And what do I do now? Let me just open a parenthesis here and introduce you to a certain kind of operator, which will make this very easy. Okay, suppose I am working in 3 dimensions, x, y, and z. And I have a vector here, r. And let me just assign a value to r. R is, I don't know, 3i plus 4j plus 5k. You see, if I just take the projection of this vector in any direction and then multiply it by the unit vector in that direction. Okay, suppose I take this r, okay, I take the projection of this in the x direction. Okay, what do I get? 3. Then suppose I multiply it by the unit vector in the x direction. And now suppose I do it for all of them. Okay, I take the unit vector in the y direction and take the unit vector, okay, dot r of the vector so that I find the y component and multiply it by that. And finally, I use k and k dot r. What do I get? Okay, I'll get my r back, right? Because I just look at each component one by one, x component times the unit vector in that direction, y, etc. Okay, so if I then just do the same thing on this vector, how do I do it? Okay, so I take this psi, okay, and find the component of this in a certain x direction. How do I do that? I take the inner product of that with the adjoint of the direction vector in the x direction, multiply it back by that direction. Okay, so I take a certain x component of this and then multiply it with the basis vector in that direction. Now if I do that for all components, okay, here I had to do it for 3 of them, but this x forms a continuum, okay, so if I multiply it by x, okay, and integrate, what do I get? Okay, well, I get the psi vector back, right? So that means this structure, this construct, okay, integrated over all possible values of that variable is going to give me an identity, okay? So not only this piece, but this piece is going to give me an identity operator. And this is going to be true for any direction that I choose, okay? So what have I done here? I have actually found a certain component of this psi in a certain x direction. But that is how I constructed this psi, right? So this term here, this piece here, this inner product is what?
It is the
Okay.
projection of psi into that.
Okay, so what's that? What is the x component of this vector?
Number.
Psi of x, right? Okay, so this is just psi, small psi of x. Okay, so you see what we get here. We get a representation in which I am adding, okay, these are the unit vectors, if you like, okay, in this basis, in the x basis of this psi of x. So these are like the expansion coefficients or the coefficients. These are this 3, 4, 5 values. Okay, the amount of x vector that I am going to have. Okay, so this abstract vector in Hilbert space is made up of these x vectors, which, okay, have contributions of psi x from each one of these components. All right, so, but I could have done this with any actually object, okay? I could have chosen any other vector, any other basis, for example, the momentum basis, and I could have done the same thing with that, okay? So I could have just used, instead of x, I could have used my variable k, so these are now eigenvectors of the momentum operator, okay? Something like this, k. So now I am working on a different basis, okay, these p vectors, if you like, okay? So now I'm expanding this psi, the same function, in terms of the momentum basis eigenvectors, okay? Inner product with psi, and that's also psi. Why? Because no matter which basis I use, this is always going to be identity. If I just have, yes.
When we say eigenvectors, we mean vectors of functions, right? Not like numeric vectors.
Okay, so now you see we are a little bit abstract. So in fact, let me just come to that question in a few minutes, because that's what we are going to do. Okay. So this is now something which goes like the k, okay, psi of x. Okay? I'm sorry, psi, not, okay, something else now. I can't say psi, okay. No. Okay, yeah, it's going to be some other function, which in fact is going to be psi, okay. So let me just, okay, let me just wait a little bit before, okay, so let me just take this away. Okay, but now how can I relate these two objects, okay? How can I, if I know this, how can I go to that, etc.? Okay, so I am interested in actually finding out what this k psi is. Okay, so let's just see what we can do with that. Okay, so I'm interested in finding out what this k psi is. I just identified this x psi as psi x. So let me just go to do the following. Let me insert an identity operator in between the k and the psi vectors. Okay? So this we are going to do a lot. Okay? So what I'm going to do is I'm going to insert an identity between k and psi, and the identity that I'm going to introduce is going to be dx. Okay, I have this k, and then x. Okay, so remember this was identity together with the integral. Okay, and then I have psi. Okay. Now, this thing here is my psi of x. Right? So I have this projection in the k direction of psi, which is given by this integral. It contains this psi x and is going to give me k psi. Now k psi, remember, if I just look at these expressions, the psi x corresponds to the wave function in x space. So if I want this thing to be parallel in all spaces, well, this thing I want to associate with my g of k, right? The expansion coefficients in the momentum space. So if I make that identification, if I say, well, let me identify this as g of k, my expansion coefficients, then you see I find the relationship between the momentum and position eigenvectors. So looking at this equation, can you tell me what kx is? If this is going to give me g of k and this is psi of x.
Minus.
Okay.
Minus I kx.
Okay, so it's going to be e to the minus I kx over square root of 2 pi, right?
How can we end up with this minus IKX times I?
Okay, we just have the Fourier transform, right? Our equations for momentum space wave function and, okay, dk e to the minus I kx over square root of 2 pi psi of x, right? dx. Okay, so we identify this term as that. Let's just check. I mean, if we have, if for example I want to find psi of x from this quantity, how can I do that? Well, in place of psi of x, okay, in place of g of k, I have this k psi, right? So this is my g of k. So if I just put in x k and integrate over all k, you see now I have my identity. The k and k together give me identity, right? So this just gives me x psi, which is exactly what I want. Okay? So you see, once you get the hang of this, this is really actually quite fun. You don't have to worry about what's happening where. These things, kx and xk, okay, are the projections of these vectors onto one another. So I'm going from one basis to another. Okay, so now you can see what this xk is going to be. In fact, it's going to be the complex conjugate of this, right? So it's just going to be e to the I kx or square root of 2 pi. All right? Yes?
What allowed us to put the integral outside of the brackets?
Which integral out of?
Couldn't we do that when we would have problem doing the same operation, taking the integral outside, because you said identity was with the integral, not without the integral.
Yes, okay, so identity, in order to have the identity, you must have a sum over all states, okay? So here, again, you see, I have this sum over all states, okay? This is just a summation, okay? I have this product of two objects. So whenever you are confused, just replace these things with what they are. So this is an integral over e to the minus I kx over square root of 2 pi times psi of x, and it's being integrated over.
So I can always take an integral outside of any bracket.
Well, where was it inside the bracket? It was never inside.
You said I'm gonna put an identity in between, but then you didn't quite put the identity in between. You put it, then you take the summation outside. But my question is, when would that not be legal?
It's always legal. Okay, so because what we are doing here, maybe I'm just doing some steps a little bit too fast, but I have something which is like this, K inner product with psi, okay? So I am inserting my identity in between K and psi. So what does that correspond to? That corresponds to K, and then I have this X, right? X psi. Okay, so all inner products here. So this inner product with that inner product with that. And I sum over these things. So these inner products are the inner product of two vectors with one another. Okay, so I can, what I don't even usually write the integral in between here because it's a sum over all possible states like this. Okay, so the summation appears outside this event. Okay, just like what we are doing here. Okay, we are summing these bunch of terms, 1, 2, 3 terms. So there are these inner products and multiplications, etc., but they are being summed over like this. Okay, so the summation is going to appear on the outside. Any questions about this? Yes.
Can you explain the last line again?
You mean where? This point here?
Yes.
Okay, so what we have here is if I want to go from g of k, okay, to psi of x, how do I do it? Okay, so what I do is I just take this g of k and multiply it by that and sum over k, then you see this piece here becomes identity and drops out. Okay, so whenever I have a structure like this, that just drops out. Okay.
So if we want to change the basis, we just the basis vectors of the other space, we form an identity matrix with them and just sandwich it between the cat and the dog.
Yes, that's it. Okay, so in fact, let's just do certain things that you know how to do already, okay? And do it in this notation. Okay, so let's just look at the case when, let me just do this before I forget. Okay, so suppose, okay, so let me just say, remember, this is something we did many times. We had this psi x0 is given, okay, it's something. And then we said, okay, we want to now convert this, okay, into an expansion. And we have this h times un is equal to en un. So these are the eigenfunctions. And now I want to expand, okay, this psi x0 in terms of these Cn uns for various reasons, right? And how did we find these Cn's? These Cn's were equal to integral of this un star of x times psi x0 dx, right? So this is something that we know how to do quite well. Now let's try to analyze this, what we are doing here in the Hilbert space. We are given some capital psi at time equal to 0, right? And I have eigenfunctions of this Hamiltonian. So H, I'm just rewriting these equations. Un equals En Un. But now these UNs, okay, they may be continuous or they may be discrete, okay? So if, for example, we have something like particle in a box, perhaps, okay, in that case, it's going to be discrete, okay? Then that's why I'm writing them as ENs. Now, I want to expand this psi x0, this function, in terms of the eigenfunctions UN. Now, what are these UNs? Okay, this UN of x is x into UN. Okay, so we are going to get, let me perhaps call these things. Okay, so let me use capital letters. Let me do it slowly so that we, okay, so H has, okay, I'm going to relax this requirement that there should be capital letters in bras and kets, but for the time being, maybe I'll just stick to it so that we know what these things are. So we have this U vectors now, which are eigenfunctions of a Hermitian operator, the Hamiltonian. So now I can expand my psi 0. So my psi 0 is some vector in this space. And these U1s, U2, whatever, U3, all this stuff are now my basis vectors. Okay, new basis vectors in which I want to expand everything. So what are these things? Well, in the x basis, I know what these things are. In the x basis, they are just these UN of x's, right? Because whenever I put something into the x basis, I get this nice x wave function, okay? That's always what I get. So now I want to expand this psi 0 in terms of these UNs. How do I do it? Okay. Yes.
You can take the inner product of.
Yes. Okay. So we take the inner product. So it's just we just put in an identity operator. Okay. We put in this identity operator, which is going to be UN, okay, summed over n. So instead of the integral now, I have summation over n because these are discrete. Okay, and this is identity. Because this just says, take the first UN component, multiply it by UN. Take the second one, multiply it by UN. Okay, so just like what we are doing there. Okay, take the x component, multiply it by I. Take the y component, multiply by y. Okay, and this in inner product with psi 0. That's it. I have found the expansion. Okay, you see this is so powerful a notation. The notation is extremely powerful and you can just do everything very easily. So this is now the inner product of this UN with psi 0. So what is that? Exactly what I have here, right? It's going to be UN n star of x psi x0 dx. Okay, so those are the expansion coefficients. But the nice thing is I don't have to worry about, okay, what form I'm going to put here, etc. Obviously, at the end, you still have to do this integral, right? There's no way running away from that. But this just tells me what these things are. So these are these coefficients, CNs. Okay? So I was able to expand my psi 0 in terms of these UNs. Now, if I want to see these things as a function, because these are, you see, it's still abstract vectors. These are ket vectors. So I'm not going to, okay, it's not, these are these funny infinite dimensional, okay, perhaps not funny, scary, okay, vectors, very complicated, etc. But I can always relate them to functions. So what do? I find the x projection of these things, okay, to the x spaces. So it's going to be x psi 0 is equal to summation n Cn x un. And those things I know are just functions. So this is just psi x0 is equal to summation n Cn un of x. Okay, exactly what I have here. All right, so this is just a nice formal way of generating all of these things. Okay, in fact, usually we'll get so much used to using these identity operators that I'm going to just use summation when I should be using an integral, or I write down an integral and I should be using a summation. All that means is sum over all states, okay? Sum over all states. It can be discrete, it can be an integral, okay? It depends on the type of, okay, variable you are using. But as long as you sum this over complete sets of states, which are orthonormal and complete, you are okay. All right? Okay. So, what else? Let's try to...
X.
Yes, okay. So, what you're saying is that if I look at the eigenfunctions of x, okay, they have the form delta x minus x1, for example, is equal to x1 times delta x minus x1. Okay, but these are in the x space, right? In the p space, they look different, obviously. Okay, so this, if I now go to, okay, so this, let's write this in Hilbert space, the operator x, okay, operating on this object, eigenstate x1, has an eigenvalue x1 times x1. Okay? So in the x basis, if I now go to the x basis, x1, well, it almost tells you what it should be. Okay? It is delta x minus x1 because this is an orthonormal basis, and that's what you get. But what you can do is you can look at what this thing is, for example, in the p basis. Okay, so how do I do that? Well, I'm going to put in, okay, so the question is, what is, I like to use the k's. Okay, k x1 is equal to what? Okay, so this is going to be the form of the eigenstate, in the momentum basis. And that we know, okay?
Transform of delta function.
Well, okay, we already looked at that, okay? Which is, okay, kx is e to the minus ikx. It's equal to e to the minus I k x1 over square root of 2 pi. So remember that in the position basis, okay, the momentum eigenfunctions are e to the ikx's, right? Remember? Okay, so if I want to write down what in the x basis a momentum space eigenfunction is, it is e to the ikx over square root of 2 pi. So in the momentum basis, the position wave function is that.
Also,
You
may I
see?
add something?
Yes.
Due to orthogonality, shouldn't we multiply square root of 2 pi instead of dividing? Because then we multiply this to that product.
Yeah, okay, let's try. So let's find out what happens if I just take two of these things, okay, and find an integral. So let me just do something like this. Let me take kx1 and another one, x2k. Okay? Integrate with respect to k. So what do I get? Because this is an identity, I get x2, x1. So I should get just directly a delta function, but let's just check. So this is going to be dk, okay, 1 over 2 pi, right? Because there's 1 over square root of 2 pi in both of them. This is x2k, so it's going to be e to the I, k with a plus x, so it's x2. This is the complex conjugate, k x1, so it's going to come in the minus x1. Okay, integrated, and it is a delta function indeed, right? So delta x1 minus x2. Very nice. Okay, so everything fits in beautifully, actually. So there's lots of aesthetics in it. It's no wonder that Dirac invented it. Unfortunately, he then thought that all physical theories must be beautiful. If it's not beautiful, it's wrong, etc., which influenced physics somewhat negatively, I must say, for some amount of time, because not all of our theories are beautiful. Okay. So perhaps this table we can extend a little bit. All right, so if I have, for example, something like F inner product with G, okay, we know from definition that this is G, okay, F complex conjugate. But the adjoint of this, you see, is going to be GF. Okay? G will go to a bra vector, F will go to a ket vector, and this is what we have. So a constant here, this is a number, okay, goes to its complex conjugate. So we can, in more general terms, write C, it's in the adjoint space, it becomes complex conjugate OC. Okay, if we have similarly something like F A G, we know that this goes to G A adjoint F complex conjugate. So since numbers, so this is the result of this is a number. Since this is a number, okay, its adjoint is going to be G A dagger F. Okay. And you can then look at this A operating on G part and separate that out. So you see F goes to its adjoint. So that must be the adjoint of that. So an operator A operating on a ket in this dual space goes to the bra version of that A dagger. Okay, so anything that's operating, an operator operating toward the right in normal Hilbert space, okay, in the adjoint space will operate toward the left, but it will go to its Hermitian adjoint. Okay, so we are going to be careful in these things, but if it's a Hermitian operator, of course, it doesn't matter. Okay, if it's something like P or H or whatever. All right, any questions at this point?
I have one about that projection operator.
Yes.
If we define, you know, the partial project, signal from 1 to k, for example, equals from 1 to n, projections to finite eigenstates. Can we say that it converges weakly to identity, but not strongly?
That I do not know. It will probably depend on the operator that's generating these eigenfunctions. Okay, so I don't know if it's going to work out in general, but okay, so there will be times where we'll be projecting out a subset rather than all of them, but at the moment we are going to sum over all states so that we will not worry about convergence or things of that sort. Okay, let's.
Definition of isn't the definition of infinite sum limit of those partial sums?
Okay, you would worry about such things only if you worry about convergence. Okay, these functions are always nice and convergent unless you work with very weird sort of operators or things like that. Okay, but I do appreciate that you have these mathematical worries about these things. In fact, there are some physicists notably famous for their mathematical precision or the search for mathematical precision in these things. The most famous one is Pauli. He did not believe any algebra until all steps were proved in detail, and he would argue that, okay, the argument is not complete unless this is done and done, etc. Okay, so the rumors are that when he died and finally went to see God, he asked him about a problem that he could not solve, and God told him the solution, and he argued that no, that's wrong. That's not the way it can be. Okay, so it's nice to be very formal and precise, but things work out nicely. Oh, okay, we are out of time. Okay, I'll let you go, and then we'll meet.